Hey AP Chemsters, this is Mrs. Vanderlei bringing you another edition of the Blank Wall series. Bells 4 and 5, this is for you. We didn't get as far as we need to in class, so we need to just kind of blank wall the rest of this. Can you get out your notes? Can you get out your calculator? Can you get started? All right, so as you are doing that, why don't I just lay down a couple ground rules again. Whenever we blank wall, you need to, if you have any questions, jot them down. I can answer them the next day, or you can always text or email me them. Also, keep in mind, if I say go ahead and do this problem, pause this. You need to actually do the problem, just don't watch me do it. And then you'll click, the play button when you're ready to go on. So hopefully you have your notes and your calculator and you're ready to go. And problem number 4, we already started this. We're looking at the relationship between temperature and volume. And we said that as temperature increased in lab, didn't the volume go up, or vice versa? If the volume increased, the temperature go up? Hopefully that is a direct relationship. And as we said today in class, if it's to direct, you're going to divide. So you have V1 over T1 equals V2 over T2. So we take our first set of conditions right here. Oh my, what's this? No idea. Why are you here? Go away. Delete. So anyway, we have temperature and we have volume. And that's the first set of conditions. But I'm looking at temperature. What did we have to do to temperature? You have to add 273, and that's where we got the 288 from. Here's our second set of conditions. And notice that again, we had to convert 38 degrees Celsius into Kelvin. So if I was smart, I would go ahead and put the little K here out. Here we go. There's my K. And so now what? Well, we need to solve for V2. So you cross multiply and divide. And what did you get? Go ahead and pause this and come up with an answer. All right, well, temperature went up. I would fully expect volume to go up. And when I did my work, I got V2 is equal to 2.79 liters, of course. So with 2.79 liters, what does this tell me? Temperature went up, so volume should go up, and it did. So why don't you go ahead and set up problem number 5, see what you get. Go ahead and pause this. All right, so hopefully you set up the equation V1 over T1 equals V2 over T2. You plugged in your values. Now, wait a second, what did temperature do? Temperature went up. So what should volume do? Volume should go up. Well, with 2 sig figs, I too have volume going up. Let's go on the next page. All right, so here's another law here between pressure and temperature. That if pressure goes up, temperature goes up. Temperature goes up, pressure goes up. The vice versa works as well. Pressure drops, so does temperature. It's a direct proportion. And once again, if it's direct, what are we going to do? We're going to divide, okay? And once again, if you're dealing with temperature, what unit must we be in? We must be in Kelvin. It is the exact same process as the Charles law, and so we have no examples for Gay-Lussac. It's just like Charles. Now, a more handy situation here is the combined gas law. And I'm going to star that because this is a much more practical use of our gas laws. That most often that if you change pressure and temperature, volume will also change. It's very difficult to keep one constant. Perhaps if you have a rigid container, volume you can keep constant, but in reality, they're all going to change. So it's P1 V1 over T1 equals P2 V2 over T2. The only requirement, again, is that temperature must be in Kelvin. Your units must be consistent. So the pressure units of 1 has to be the same units of pressure number 2. So let's go ahead and you solve for problem number 6 and see if you get what I get. Go ahead and do that. Pause this, do your work, see how you do. All right, so here's my setup. Here's my equation. Notice they gave you mils both times. I had to convert into Kelvin. And before I give you my final answer, let's kind of think about what's going on here. So we're looking for a new pressure. Well, what's happening to volume? Volume's going from 500 with 2 sig figs. I converted scientific notation to regular. So 500 mils to 25 mils. Volume went way down, okay? What would that do to pressure just alone? Well, if volume goes down, pressure goes up, okay? So I should expect by volume a higher pressure. Well, what about temperature? Here we go. Temperature also went up. If temperature goes up, pressure goes up. So I have two relationships that's going to drive pressure to go up. So there's no doubt in my mind that pressure is going to be bigger than 710. Let's see what you get. And wow, look at that pressure, 51,000 torr. That is a huge pressure. That's yeah, pressure went way up. Okay, so it makes sense in my book, so I think we're good there. So again, if you have any questions, let me know. We have another law, Avogadro's law. So if a given quantity of gas is held constant pressure, then volume is directly proportional to the number of molecules or moles of a gas. So in other words, volume goes up, moles go up at constant pressure. It's like blowing up a balloon, right? When you blow up a balloon, what are you doing? You're adding more moles, or in a sense, molecules of gas into the balloon. So as you blow up a balloon, you have more molecules. Duh, what happens to volume? It goes up. What happens if you let go of the balloon? It makes that little noise, right? So then what? Oh, what's that noise? It's a noise that moles are escaping, molecules are escaping. What happens to your volume? It goes down. This is a direct relationship. So what are you going to do? You are going to divide. What's N though in this case is the number of moles. So we don't have to worry about Kelvin here, and temperature is not part of the issue. What do we have to worry about is moles. Moles can show up in many different forms. I can give you molecules. I can give you grams, periodic table. Oh, thanks, awesome chocolate. Where else can we get moles from? Hopefully last chapter taught you something. You can get it from a BCA table. So let's look at problem number 7. Okay, it says, suppose we have a 12.2 liter sample containing 0.5 moles of oxygen gas at a pressure of 1 atmosphere and a temperature 25. If all of this oxygen were converted to ozone at the same temperature and pressure, what would be the volume of ozone? Well, you need to know the moles of ozone. And how are you going to solve for moles of ozone? It says write the equation first. Let me do that. So oxygen is being converted to ozone. What we do next, we need to balance it. I bet a BCA table will tell you about moles. So I start off with 0.5 moles of oxygen. What did the problem say? If all of this ozone right here, you see that? Oxygen were converted to ozone. Oh, so that means I have no more oxygen left. What does that mean? It was all converted into ozone. So 0.5 divided by 3 times 2 is 0.3. So what does that 0.33 represent? It's the moles of ozone. So I think we're ready to rock and roll. We're trying to find volume of ozone. I have volume of oxygen. I have moles of oxygen. I have moles of ozone. You can solve for V2. Why don't you pause this, finish off the problem, and see how you do. So this is my setup. I hope you got something like that. Before I give you the answer, let me kind of explain to you how I would do this as mental math. You see this 12.2 is divided by 0.5. Well, that's the same thing as saying 12.2 divided by 1/2, which is the same thing as saying 12.2 times 2. Let me try that again. Let me show you what I mean here. So I have 12.2. Is it 0.5 equal 1/2? Yes. So what do I do with my denominator? I need to rationalize it, right? So 12.2 times 2 is roughly 24. That's equal to V2 over 0.33. What do I know 0.33 is a third? So V2 is really roughly a third of 24, which I know is 8. If you do your actual math using your calculator, don't you get 8.1 with 2 sig figs? Yes, you do. I'm awfully close. Okay, but I was just trying to show you with mental math how I've gotten awfully close to that answer. All right, let's go to the next page. All right, so there's the four quantities to describe gases. We have pressure, volume, temperature, and moles. Up until now, from 5.2 and 5.3, we've been talking about if something's going to change. So are conditions changing? So if I have this set of conditions, I change volume, how is pressure going to respond? Or temperature, whatever. The ideal gas law is where nothing's changing. It's a snapshot. What's happening right now with these conditions? So if I know what pressure and volume and temperature, can I solve for moles or something? The answer is yes. Now, do you remember you have this symbol right here? What is that symbol? It means it's proportional to. That means there's a constant involved. And so if you're using the ideal gas law, all right, that proportion, or excuse me, that constant, that K, is replaced with an R. So when you use the ideal gas law, R is that K constant. Combine them all together. So here we have unit K. When we talk about that proportion, so volume over moles gives you a constant. Volume times pressure gives you a constant. Volume over temperature gives you a constant. That's that K value that you had to solve for in your lab. But if you are using the ideal gas law, that K becomes R, where R is that number. It's a constant. That number doesn't change. Now, something that you have to be really, really, really careful with is the units. R must be liters atmospheres over mole Kelvin. What does this tell me? My volume must be in liters. Did you write that down? Pressure must be in atmospheres. Moles are moles. Temperature must be in Kelvin. So you write this down. It's important. So volume must be in liters. Pressure must be in atmospheres. Hopefully you know what temperature must be. Hopefully you knew that moles was mole. So let's check this out. Look at problem number 8. A sample of hydrogen gas has a volume of 8.56 liters. Check, that's good. A temperature 0 degrees and a pressure 1.5 atmospheres. Calculate the moles of hydrogen present in the sample. Okay, so what equation use? Hivner, you can do it. Go ahead and pause this and solve. Okay, so here's my equation, and I plugged in the numbers. What I want to show you here is look what happens to units. Liters, cancel. Atmospheres, cancel. Kelvins, cancel. What's left? Moles, and that's what you're looking for. So go ahead and actually solve for moles at this point. All right, so there you go. There's your number of moles. Notice I have 2 sig figs because of pressure. Now, before I go on to problem number 9, let's think about this equation of PV equals nRT. Okay, so if you have any other pressure besides atmospheres, we already know how to convert it. If you have milliliters or cubic centimeters, I hope you know how to convert to liters. But what about moles? How might you arrive at moles? Like we've said before, if I give you molecules, can you solve for moles? Yes. If I give you grams, periodic table, yes, you can solve for moles. Perhaps you might need a BCA table to solve for moles. So be really careful and look closely at what you're given. So speaking of that, here's problem number 9. Calculate the volume of 525 grams, periodic table, of oxygen. We have 25.7 torr and 25 degrees C. Good heavens, you have to fix everything. Why don't you take some time out, pause this, and see how you do. All right, so I went ahead and solved for moles, I saw for atmospheres. So my next time, I'm going to erase what I have written and just use 16.4 and 0.0388. Okay. Let me go on and continue the problem. Oh, I also convert to Kelvin. All right, so here we go. This is what I get for an answer. I sure hope that's what you get for an answer. Does this answer make sense? Well, number one, I have a very low pressure, so if pressure is low, volume is going to be high. Okay, I'd say it is. If moles are high, then volume will be high. Okay, it is. So I have a double whammy. Temperature is fairly average, so that's not going to really affect it too much. But between a very low pressure and a very high number of moles, I have a very large volume. So I'm going to quit right here. We're in about 16 minutes. So I hope this is helpful. And again, if you have any questions, text me or email me, and I'll do what I can. We'll see you tomorrow. Bye-bye.